Okay, hi everybody. We're moving on to part C, and we're talking about mapping quantities and the different maps that we can create with different quantities. So let's dig in. The first thing I just want to kind of talk about the roadmap. These are the different cartographic techniques we're going to talk about. Isopleth maps, you have seen these a million times. Isopleth, you're very familiar with these as well. I'll show you if you don't believe me. Dot maps, proportional symbols, cartograms, and I dropped flow maps, so ignore that one. So Isopleth maps. This is your typical population, political maps, where you have a range of values that are classified, and then those classes are represented by some color or shade on the map. You've seen these a million times. Here's one example. Here we have counties and the total acreage that's been harvested for forage. So Isopleth comes from the Greek koros, meaning place, and pleth, meaning value. So it's a value associated with a place. You need to be really careful with Isopleth maps and think about whether or not the data should be normalized. You definitely want to have well-defined enumeration units. You want to be using discrete data, so vector data, not continuous data like rasters. The discrete data is defined by a specific enumeration unit, right? We've got political subdivisions or study sites or whatever it is. It has a defined unit. You really have to have that for Isopleth maps. So you can map totals. So the problem with that is that the different sized unit is going to maybe distort the data presentation. You might want to normalize. Like I said, we'll talk about that in a second. Derived values are more true representation probably when you're dealing with Isopleth maps. You want to deal with ratios or densities, and that's what I mean by normalizing. Instead of having the population per a county or a political unit, you'd want to have people per square mile or people per acre or people per square meter, so that you're using a consistent area instead of a random kind of area like this. But yeah, normalizing would be smart. Totals can be a little bit distorted. Okay, so you do have to classify to do Isopleth maps. And you can see that here. All right, so this is a good example of when to normalize, not maybe as good as your typical GDP or population densities, but again, if this is forage, pure forest harvested acres, so a hard number, but if you have a large county versus a really small one, you'd expect there to be some correlation between the size of the county itself and the total number of acres. So if we normalize this data and actually talk about it in consistent units, right? We want to adjust the value for a number that's measured on a differing scale, like county size, and transfer it to a number that's represented by a common scale. So the total number of acres, well, I guess people are easier for me to talk about, but if we talk about GDP per capita or people per acre versus people per county, you get rid of that, the correlation between a larger county size. Okay, that was really, really well said. Sorry about that. All right, Isopleth maps. Again, you've seen these 1,000 times. You've probably made them. Every time you make a contour map, an isopleth line is a line where all the values along that line are equal. So contours, isotherm, heat maps, temperature maps, precipitation maps, isolines, isopleth, those are all related terms. Yeah, it's a line of equal value joining all the other places of equal value. Contour lines are the most common, so everywhere along this line is 11,000 units of elevation, right? And then you can read up or down from there depending on the other labeled contour lines. So connecting places of equal value. Isopleth, you do generally have to interpolate the surface. So when we're dealing with precipitation, we have weather stations scattered around here where we have known values. Interpolating means we have to create new data points between known data points. And then we can create these isopleth or isotherm or whatever you want to call them lines, connecting places of equal precipitation and then we can go to places where we don't have known values and estimate or interpolate those values. This is an Isopleth map of H1N1 deaths in California. Again, we probably have cities or counties reporting in deaths, and then we have to create values in between known values and create these isopleth lines of equal value. All right. So dot maps and dot density maps are a really great way of showing spatial distribution. The one caveat is with ArcGIS, it takes your enumeration unit, whether it's a county, city, census block, whatever it happens to be, and it takes the number of dots and randomly scatters them throughout there. So when you're dealing with really small areas, it tends to work better. Here you get the overall spatial distribution in Maine by county, but if we were to replot these dots, all of these guys would come out in a different place. So they're not marking spatially true locations within each enumeration unit. It's random, but the overall pattern maintains. The other thing to think about is when you're creating side-by-side maps in a figure like that, you need to be really careful that one dot, if it doesn't equal the same amount, and I can understand why they wouldn't. So here we're dealing with enrollment in Maine, college enrollment by county, by gender. And here, for females, one dot equals 150 females, and here, one dot equals 25 males. That's a little bit misleading if you bury this information. I can understand why you wouldn't want one dot to equal 150 males, because this would just, most of these would just be colored in solid blocks. If one dot equaled 25 female, I'm not sure. I'm sure that they messed around with it and did this on purpose. But I think you'd want to really highlight this and make sure that it's very clear to your viewer. But anyway, yeah, so random placement within each enumeration unit. So the advantages of dot maps, they're very easy to understand. You get a great sense of the distribution patterns, and you can map more than one variable at a time, and you could do that by overlaying it on top of a Isopleth map or something like that. This is an example of how you have the same enumeration unit, and one time it plots up this way, and the same number of dots might plot up this way the next time. So if you don't like the way it plots, take the data out and reclassify it and see if you like it better the next time. I've been known to do that. So random placement within the unit. If you go with a smaller unit, you're going to get a better result, I think. I'm going to let you read through these things. It's just a lot of kind of technical information about dot placement. You can go ahead and pause it if you want to read. This is one way to get around it, where you've actually got densities or normalized data per county, but you don't show the county lines and just show it per state. It's one way of kind of preserving the densities largely where they're supposed to be. So we're clumping things around where we know the populations to exist. And we can do that using county data versus state data, which would just give you a random scattering throughout the state. Okay, proportional symbols. You've seen these before. Larger symbol, larger value. You can do multiple things with these. This is just pure traffic fatalities by state. I think the student made them transparent here just because they overlapped so that you wouldn't lose track of what's going on. But you can see in this next example that it's pretty easy. I'll show you that in one second, to show two things at once. So graduated symbol, proportional symbol, they're the same thing. The symbol varies in size relative to the quantity it's representing. Yeah. Density would be done in a Isopleth map or dot density, whereas magnitude, like an actual ratio, a total, or proportion, can be done with proportional symbols. Okay, so here we've got a Isopleth map showing us ACT scores in the background, and then the percent of college-bound seniors on top of that with a graduated symbol. So it's kind of a handy way of being able to show two different quantities at once. A relatively clean way, I should say. Okay, so the last kind of map I want to talk about is a cartogram, and if you guys are interested in doing that this semester, let me know. Shoot me an email, and if enough people get back to me, we can build a lab about this. I've never done it myself, but I know there's tools out there and there's free software to do it. But the cool thing about a cartogram is it gives you an accurate representation per capita. It normalizes the data and gets rid of the kind of unequal spatial area and concentrates it more on a normalized result. So here we have the number of Starbucks per capita by state, Walmart and McDonald's. It does get tricky though, because the states that aren't participating don't have Starbucks kind of go away. So sometimes it can be really misleading or just confusing for people to look at. But I'm going to show you some other examples. This is the classic example of where a cartogram comes in really handy. 2008 election results, just purely by state or by county, if we simplified it, which way they swung, red or blue. Here the red tends to look like it's dominating, so we might be surprised by the outcome of the vote. But if we look at it in a cartogram sense and actually look at the numbers of people that are in these places voting Democrat versus Republican, all of a sudden it looks like a more true representation of how the election actually turned out. The red, when we're talking about the actual numbers of people, tends to shrink away, and we've got the higher populations of people spreading out spatially and being represented more accurately by the number of people. Okay, so here's a fun game for you. I pulled a bunch of random global cartograms. You try and tell me what's being mapped. This first one's going to be almost impossible, but start looking at the patterns. Who's really trumping? Who's big? Europe is going a little bit crazy. United States are holding their own. This is a per capita cartogram of alcohol consumption. And here comes the second one. So notice that the Americas have pretty much disappeared. Africa is quite bloated. Europe is largely gone. India's got some problems. Any ideas? This is the prevalence of HIV. Shocking. I mean, it's not shocking, but man, what a powerful way to display this data. All right, how about this one? Bloated, terribly bloated. Europe is holding its own. Africa is gone. South America is largely gone. Brazil is hanging in there a little bit. Yeah, what do you think? Military spending makes perfect sense. All right, how about this one? Wow, what are we doing? What are we doing? And Europe, Great Britain, goodness. What's going on here, do you think? Yep, I think it's mostly McDonald's. I really do. I think it's Happy Meals that's making this happen. So conversely, not to give it away, but then what's going on here? I'm not even sure Canada is in this one, or maybe the United States isn't in this one. What's the other color? Oh yeah, so the United States is actually gone, and this might be just Canada or Mexico. Oh, Mexico's gone here. I'm not sure what that is, but anyway, so yes, this is toy exports. All right, wealth of nations, interesting to look at. Around the 1500s, Europe is strong. We've got a lot of strength here, but when you go to 2002, things have sort of equalized a little bit in the northern hemisphere, I should say. Interesting maps. So cartograms. No data is lost through the classification. We're dealing with a strict spatial normalization. You can tell quite an interesting story and show distributions that might otherwise be obscured by your classification. The cons are they do look messy and they do look relatively inaccurate unless you understand what's really going on. The logic is complicated, and sometimes you just lose track of things because of the distortion. You also can't go back from that and like compare the color or the size to any kind of a legend, extract actual information, so that can be frustrating. Finally, I just want to say in 6910 we do a really quick arc scene exercise where you can extrude data, and we don't actually do this. We did go in and drape some things in arc scene, but I challenge you guys to go into arc scene. If you can take your populations, here's just strictly whether the county went Republican or Democrat. If you take that same data and plot it up in arc scene, you can extrude the elevations or heights of those polygons based on the population density. So again, we're talking about either densities or actual totals of people, but it really helps understand why elections might go the way they do. If you look at it strictly this way, it is really not representing the populations. So we can start accounting for the numbers of people in these very small places by extruding the values. So this is something you can do in arc scene. And again, if anyone's interested in making maps like this and can't figure it out on your own, I can send you some tutorials on how to do this. So that's it. 2 more little briefies like this, and that's it for this first module. Thanks.